of presentation, I really like these slides because it's present the ARPANET, the beginning of the internet in 1978. And as you can see in this slide, there is also an interesting video on YouTube from Professor Kleinbrock explaining how they built the first version of the internet. And as you can see here, there are few nodes connected with different type of communication. Some of them are satellite communication and so on. But the point here is to show that since the beginning, the idea of internet was to connect things to the network. Step by step, these few nodes became much bigger, massive amount of nodes, servers, and in general, this is a tentative or represent the internet and the web right now. So we moved from a few number of nodes with a few type of connectivity to a massive and huge ecosystem with a lot of services and providers that you of course know. So this is the first step of the history. So the internet, the web, and then we had another huge change in the information technology ecosystem. And this change is the mobile-centric, the mobile revolution that you probably living right now and you have seen. But in order to understand how these numbers can change the architectures and how services are shaped in order to support new application, new deployments, and new use cases, I like to show these additional slide. Here you can see two completely different events, but the point here is to understand how quickly the number of connected devices is increased over the last 10 years, we can say. On the right side, you can see a comparison between the Pope announcement in St. Peter's Square in 2005 and 2013, and the difference is amazing. I mean, you can see in 2005 we have a few telephone, a few lights from the screen. In 2013, everyone has a smartphone, a tablet, taking pictures, taking videos of a such important event. The point here is to understand how mobile computing, how they are pervasive, how the smartphone and mobile devices are pervasive in our life. And if you think about the infrastructure that we need to support all these devices is completely changed. The cellular network, for example, completely changed from 2005 and to 2013, not only in terms of bandwidth, but in terms of capability to support this massive amount of devices. The other example is related to 2017, the concert of Vasco Rossi at Modena Park, where we had 230,000 devices connected in the same area. As you can see here from some data coming from Telecom Italia and Olivetti, how these devices were moving from the different cities in Emilia-Romagna. But the point also here is that now we have an infrastructure capable of handle thousands of devices in the same place at the same time, sharing content, real-time content, multimedia content on the network. So this is a massive change, a huge change in the architecture. But the question now is, what is the next big thing? The next big thing is IoT, of course. IoT is changing how architectures have been designed over the last years. And the aim of this presentation is to show you the last trend in this ecosystem and how we can try to build intelligent IoT architecture. Some interesting points about IoT. First of all, the numbers. You already seen the huge numbers related to IoT, billions of connected devices and so on. But some aspect of IoT is that already started transforming directly or indirectly several markets and fields, technological fields. IoT has a direct impact to communication. Think about cellular networks or other IoT-related technology like narrowband IoT or LoRaWAN. There are several types of connectivity. Then in terms of architecture, we will see today edge computing and how edge computing is important. IoT is changing how people are interacting with devices, so how we can say the human-to-machine interaction. And of course, industry, markets, and the whole ecosystem is changing thanks or due to the IoT. Another point from my point of view is that IoT involves several different technologies and fields in terms of skills and research. So, for example, it means computer science. IoT needs software engineer, networking and communication system, distributed system, artificial intelligence, electronics, business, and so on. So, in order to create a complete and real IoT ecosystem, all together we need to collaborate to create something really useful for everyone. Of course, the market can be quite different. In the picture on the left side, you can see connected vehicles, maybe autonomous vehicles in a few years, smart home, smart cities, of course, industrial, and connected health. So some of the markets that are interesting for the IoT. But before starting talking about my research activities and in general some of the cutting edge technology that are characterizing IoT today, I would like to highlight some of the challenges that we are facing when we talk about IoT. And I mean facing in terms of research, in terms of deployment, everything that is running around IoT right now has some important and relevant challenges that some of them are still open from different point of views. First of all, we have the connectivity and the connection issue, how we connect our devices in order to be to talk and send and receive data and implement their behavior. Another big issue is the heterogeneity management. We have a massive amount of producers, operating systems, software, protocols. The heterogeneity in IoT affects all the layers of the stack. Okay, so it is really important to understand how to handle heterogeneity, and we will see how maybe digital twin can bring something really interesting about that. Of course, interoperability, security, how we collect, we generate, we process data coming from all these heterogeneous sources. The adoption of standards. We have some standards, but it is important to understand how to use them and where we can adopt them. And all these challenges are augmented by the possibility to have real-time application and real-time capabilities for our deployment. Talking about heterogeneity, I would like, before starting speaking about digital twin, is to understand the market right now. There are a lot of application verticals that are tagged as IoT, but are they real IoT? Or are they just M2M application, machine-to-machine application? Or are they just vertical silos where the technology is closed in some business-oriented application? Here you can see some of some common cases. You can see HomeKit from Apple. It is a great system, but it is closed. It is closed. If you want to join, to add some devices to an HomeKit device, you need to buy certified devices, and they are not certified because they are using standard protocols. They are certified because they are using Apple Bluetooth chip to connect to the network, for example. Or the same thing is to Alexa. I hope to avoid to trigger some of your Alexa home devices, but then you can see the Philips Hue lighting system. These systems are great, but they are closed. So the message is, IoT is everywhere. Everyone, every company has an IoT device. But are they really IoT? Are they interoperable? Are they standard? The answer is not always. So it is important from my point of view to give you some elements to understand what is IoT and how we can create a real interoperable application. So the next point is how to identify which are some of the IoT pillars. I added another word, intelligent Internet of Things. So which are the pillars to create an intelligent IoT architecture or an intelligent IoT system? There are several aspects, as I introduced before in previous slides. IoT involves different technologies, so here I just summarize some of the pillars that I believe are important, but there are many others. Okay, among them we can see, of course, we can start from the business point of view. One of the problems of IoT is the business model. How can I can sell IoT? But it is another topic. Of course, artificial intelligence. It is really important to extract value from data to allow a IoT application to be autonomous in taking decision and react to external event. Then we have another pillar, that is the networking and connectivity. And related to how we connect and we handle connectivity, there is the point of software-defined networking. So how we can, through software application, dynamically control networking. It is something that we are doing right now for cloud computing, but it will be really important also for IoT application. Then we have some pillars coming from software engineering, software development, for example, related to how we can shape microservices to better design IoT application. Related to microservices, we have how we orchestrate IoT application in a distributed scenarios. And then I have highlighted three additional pillars that, according to me, are really important and are related to the topic that I'm trying to address with my research at the moment. The first one is an effective cyber-physical interaction. So how the physical world can effectively interact with the digital world. And this topic will be the first one, and is related to digital twin. The second one is how we can create intelligent distributed architecture. So how the architecture of IoT is changed and evolved over the last 5 years, we can say. And last but not least, another fundamental pillar is interoperability. How IoT application and system, heterogeneous application, a different application, can work together as, for example, we currently do with the web application. Okay, now web application can interact easily with each other thanks to standard and thanks to interoperability. This aspect is also another huge and important pillar for IoT. Okay, I believe that after this introduction, this motivation, we can start addressing the first point. Okay, one of the first pillar that we are going to see today is how we can effectively create an interaction between the physical world and the digital or cyber world. The first element and the most interesting element at the moment to handle the interaction between these two counterparts are the digital twin. They may have different names. We can call them digital twin or digital replicas of virtual objects or shadows. That they have different names. The idea is that we can create a digital or a virtual replica of a physical asset, replicating all its resources, characteristics, and behaviors. So in these slides, you can see a physical device, for example, a vehicle that has many sensors and actuators on board, such as the cameras, the GPS system, the engine, the sensor on the engine, a battery, if it is an electric vehicle. And this physical thing can be mirrored into a digital replica that will receive in real time all the data coming from the physical asset. So it will mirror the video from the cameras, its location, the sensors, battery status, and so on. This synchronization can be implemented using different technologies, different protocols. We can have telemetry events. We can have a request response like RESTful interaction. We can use HTTP, WebSocket, MQTT, MQP. Many protocols. The point of digital twins here is not to talk about protocols, but to talk about the concept of digital twin. The idea is that through the possibility of mirroring a physical object into a digital replica, we can do more with the object. We can do better with the object in terms of interoperability, in terms of standard adoption, in terms of how we can add additional services on top of the digital twin. For example, as you can see in the picture, we can connect the vehicle to external services. We can provide artificial intelligence on top of the data coming from and thanks to the digital replica. We can add caching system. We can add more APIs. We can connect, for example, to external services like an ERP infrastructure and so on. The idea, the concept of digital twin has been around since the beginning of 2002. It comes from a researcher from the University of Michigan. And at the beginning, it was mainly associated to the management of the product life cycle. So how I can design a product, how I can simulate a product. But step by step, and thanks to the IoT revolution, the digital twin has become cost effective to be implemented. I can easily implement a digital twin. I can handle the computation related to a digital twin. And it is one of the main topic, the hot topic for IoT in the last years. And at the moment, almost every big platform, IoT platform like AWS, so Amazon, GCP from Google, or Azure from Microsoft, they are providing their own version of a cloud digital twin. Then we will see how this term cloud digital twin means something specific, and how we can extend the concept of digital twin to work at different point of the architecture. Okay, how can we use digital twin? Of course, the digital twin is a generic concept, not only related to IoT, but in these slides we will go through the idea of digital twin, and we will try to define, to shape how digital twin are related to IoT. But as a generic reference, digital twin is a generic concept. The idea is that a twin, a digitalized version of a physical object, can help to track the history of, for example, industrial machines using real-time data in order to understand the context, learn, and possibly take a decision about the data coming from the field. Can be used to test and build new product or equipment in a virtualized environment. So you can create a clone of a physical device and try to interact with this object in virtualized environment, for example, through augmented reality or other way of human-to-machine interaction. Digital twin can be also used to simplify the interaction between the physical object and external services. They can allow to increase the security of a physical object, essentially proxying all the information. We will see how it works with IoT. Essentially, the idea is that I can protect the physical assets thanks to the digital twin, since all the requests will go through the digitalized version before reaching the physical device. And this is a way to protect and to add security, for example, to a physical object. And the other connected advantages is related to how we can extend the feature of a physical object, adding new behaviors, how we can, through the digital twin, we can, for example, manage and handle the data generated from the physical object. There are objects like IoT devices that can be changed, where the firmware can be updated. In these cases, we may take a huge advantage from the digital twin, since we can extend the capabilities of the original asset. But it is true also for updating the new devices that can be digitalized, and we can interact. We can start interacting with their digital version. Also, as we saw before for the IoT, digital twin concept involved different technology at the same time. So it is not just a topic related to one field, to one research and development field. Digital twin involves the use of APIs, so application programming interfaces, and in general open standards that allows to extract information, to automatically create digital twin, to allow the interaction among multiple systems. We need artificial intelligence, because through digital twins we will have access to a lot of data. So we need to analyze them, we need to extract value from this data, and of course artificial intelligence will be one of the pillars of the IoT, and of course also of digital twin. Then twins can be related, as I said before, to augmented and mixed reality. We can build systems that are interacting through the digital twin in a virtualized environment. And last but not least, digital twin has a huge relationship with cloud and edge computing. We can have twins on the edge, twins in the cloud, and it is really important how they can interact. We will have multiple replicas of the same physical object in different places according to the type of application that we are going to create. And of course, the last technology involved is IoT. Okay, so we can significantly adopt digital twin in IoT context. To continuous monitoring data coming from real asset, to provide intelligence to devices, to handle heterogeneity. They are absolutely a perfect fit for IoT applications. Okay, after this introduction, I would like to show you some of the some properties that characterize the digital twin. There are several properties. I took them from a really interesting survey about IoT digital twin from Roberto Minerva. I added the reference in this slide. There are several properties and characteristics, but I would like to focus on four main aspects of digital twin. But first of all, we can start from the definition. Okay, the idea, as you can see also in the picture, is that a physical object can be virtualized through its digital replica. We can call in this slide. I mean, the idea is that the definition digital twin, refers to two parts: the physical object and the logical object. So the logical object is the digitalization, and the digital twin is the composition of the physical part and the logical part. As I said before, we can add, we can change names. We can call the physical asset as device, as artifact, as object, as product, but the concept is that it is the physical thing that we are trying to virtualize. On the other end, the logical part refers to the virtualization, and we can call it logical object, digital object, clone, counterpart, companion, mate. Essentially is a software component, an agent, a software agent that is responsible to communicate with its physical counterpart. Okay, so we need to create a software that is capable of handling this relationship with its physical part. Okay, as I said before, there are different, we can say, qualifying properties related to digital twin that can be derived for the state of the art, from the application that are already available and that use digital twin. But the main four points that I would like to underline and to analyze with you are reflection, replication, composability, and augmentation. Okay, so we can start with the first one, that is reflection. So it is quite simple. The idea, the reflection capability of a digital twin is the possibility of the twin to reflect and to essentially copy all the relevant value or resources associated to the physical object and univocally represent it in the mirrored object. When I use the term resource, I mean an IoT resource. For example, a temperature sensor is a resource. A humidity sensor, a switch, a trigger, an engine, everything can be modeled as a resource. With the reflection, we take all the relevant value. It doesn't mean that we have to mirror everything. Okay, if we need to create a digital twin that is targeting a specific application, maybe related to an industrial monitoring, we don't need to mirror everything. If we need just temperature sensor, we can create a digital twin only for that data. Okay, but from a conceptual point of view, the reflection is the possibility to describe a virtualized object that has all the characteristics, resources, and value from the original physical asset. We can try also to model it. We can say that a physical object is described to a set of variables took from a space, and essentially there is a function that essentially transform the value from the physical value from the physical version to the digital one. So essentially, the digital twin is implemented through this function that has the responsibility to take the original value and potentially change it, or we can transform the value, or we can keep the same. We can have essentially two types of reflection. Sorry. In the first case, as you can see in the top right corner of the slide, we have essentially so one value from the physical will be mirrored in one value from of the digital. So the function takes only one parameter. Okay. In the second case, one or more values from the physical device are used to determine the value or a state of the digital twin, of the digital part. So the idea is that, for example, I can create some complex activity on the digital version. So, for example, using the raw data, so the data that I have from the physical part, from the physical component, I can analyze them, I can transform them, and I can expose them in a different version, or I can expose something that I haven't before. Okay, so we can reflect something, keeping it as the original version, or we can augment it, we can change and transform it. Another point I think that is really, really interesting is the time. Okay, the time concept. As you can see, the last sentence is asserts that the attribute of a digital twin depends on timestamp, location, and the original value. What does it mean? The idea is that the digital twin can change its behavior according to the value, the original value. Of course, I read a temperature value of 21 degrees. Okay, this is the original value. But it can change according to the location. Where is located the digital twin? Is it on the edge? Is it in the cloud? Because maybe on the cloud, I don't need the real-time data. Maybe I can average the values of the last 10 minutes. But on the other end, on the edge, I need the real-time information because I need to react in real time to the temperature changes. So we may have different values according to the original one, according to the location, and according to the timestamp. Why the time is important? Because we can think to reflect digital twin at different historical times. For example, we can have a digital twin of the past that essentially is trying to analyze the behavior of an object starting from the historical data that we have collected. So the time of the data is the past. Then we can have the current version of the digital twin that is analyzing what is going on right now, but we may have a digital representation of the future of the physical object. For example, through prediction, through simulation. So starting from the same physical object, we may reflect different digital clones. Okay, this is really, really important. So we can change, we can reflect according to the value, we can change the value, we can keep it the same, we can change it according to the location or to the time. Okay, so this is the main concept behind reflection. So you can start understanding how digital twins are powerful. We can shape, we can design our system based on digital twin. And another aspect is the replication. The replication of the digital twin is the possibility, the ability to replicate an object into different environment, into different replicas. Maybe also the same replica. Okay, so it's not about how I change, how I reflect the value, but how many copies of the digital twin do I have? For several reasons. Maybe I have a multi-cloud infrastructure and I would like to mirror my clone on different data centers. It works on the cloud, but it works very well also on the edge. I have multiple external application that is interacting, that they need to interact with the physical object, and I don't want that they can access the physical asset, so I can create one replica for each service. Okay, so I can improve security and expose to the external service only that specific replica. So essentially, the idea is that I can virtualize a software version of the physical object and create multiple and clone it as much as I need according to the deployment. Of course, when we talk about replication, we can introduce to digital twin different aspects related to coordination, orchestration, how we can distribute, how we can allow the communication among twins. And you may think that a digital a digital object can be seen as an agent, as a software agent that has the responsibility to replicate the physical device. The replication can be one-to-one. So we can have direct synchronization between the replicas and the original asset, or can be a master-slave synchronization. So where we have a master digital twin that is the only one responsible and to talk with the physical device, and then it will allow the synchronization with other digital twin. So starting from this point, you can also understand how digital twins are important to control the asset, the access to the physical device. Okay, is true. Thanks to the digital twin, we can protect, we can control how services and application interact with the original device. Replication can be also used to handle real-time requests, to do load balancing, and they can take advantages from many fields, from many research activities and innovation, for example, related to microservices, how we can scale according to the number of requests, according to the data center, how the application is distributed. So the idea of softwareizing a physical device and allow its replication open to other possibility and functionality that we can receive from existing fields and existing technological assets. Okay, the third interesting characteristic about digital twin is quite simple but interesting at the same time, and it is composability. The idea is that we can think to digitalize a simple object, for example, the GPS of a vehicle, or we can decide to digitalize the entire system. A car, a vehicle, is not a single digital twin, but can be seen as a composition of multiple digital twins at the same time. And maybe we can use different twins according to the use case. I'm creating a software that is monitoring the movement, how a vehicle is moving. So I'm just interested, for example, to receive GPS information and battery level information, because my target is only that. So I can compose the vehicle just with the twins that I need. So the idea is that complex scenarios can be modeled using the composition of multiple twins. And this is an open challenge, since we need a way to define how twins are connected, how twins are related. Of course, we can have digital twin of a single component, for example, a sensor, or a complex environment. Another example is a smart building. A building can be modeled as a huge digital twin that at the end is the composition of multiple twins, one for each floor, one for each room, and one for each device that we have in a smart environment. And as you can see, through digital twin, we can create decoupling the responsibility. Okay, we have the physical assets and we have the digital, and then we can compose the digital assets to create new services. Of course, composability is interesting in terms of software. The possibility of digitalizing a physical object into a software agent opens to interesting topic and open topics and challenges related to digital twin, related to software composition, how we model software component to be composed. So everything that is related to virtualization technologies, microservices, containers, communication among microservices. It is an open field at the moment, and I believe that it is possible to innovate and do some interesting research in this topic, in the digital twin world, also for this reason. I mean, the composability is a really interesting topic related to digital twin. Okay, the last property that I would like to share with you about digital twin is the augmentation. The idea is that through the use of digital twin, I can extend the capability of the original object. And this is really important in general for digital twin, but it is absolutely true and useful for the IoT. There are several objects that use and speak custom protocols, domain-specific data formats, or they can't implement security protocols. If we have a light bulb connected, it is quite hard that this light bulb with a small and tiny CPU can implement and process security algorithms. Okay, so how we can extend this capability, how we can create a secure layer, an interoperable and a uniform layer. We can do that through digital twin and through augmentation. The idea is that thanks to digital twin, our virtualized object can talk multiple protocols at the same time. We may need that an application interacting with a smart object can use a RESTful interaction, and so we can use HTTP or we can use CoAP. But at the same time, we have another application that is pub/sub oriented, and maybe we need MQTT. Okay, but the original object is talking a custom protocol. How we can handle it? We can handle it thanks to the digital twin. The twin is responsible to talk the custom protocol, but it allows to expose to the external world only standard and uniformed protocols and data format. This is a killer feature for the IoT. Okay, this is this is a smart way to handle heterogeneity in IoT ecosystem thanks to the capability of digital twin. We can easily extend the possibility of physical asset thanks to their softwareized version. And of course, it is another open point, and this is one of the aspects on the one that we are working on at the moment. So I think that this is a good introduction about the digital twin, and we can move forward and see how we can use digital twin on the different pillars. But the last slide about digital twin is related to how this virtualization space of the digital twin is changed. If we see the initial picture is completely different. We have the logical object, we have the initial representation, but then we added APIs, we added augmented functionality. We may add historical data, so storage capabilities on the twin. So the digital twin is not a simple component, can be really complex, but can be really powerful at the same time. And from a software point of view, it is really interesting how to model a digital twin in a way that they can be used as independent software agent or independent microservices to cooperate together to implement and reach the business goals that we may have for IoT application. Okay, so we have seen how digital twin can support us for cyber-physical interactions. Now, the next pillar, according to me, is how architectures can be intelligent. You already have received some information about edge computing, how the computing is changed across the last decades. I like these slides because it allows me to summarize what we have seen. We started, the computing cycle started with mainframes. Then we have a huge development of the client server application. And during from 80 to 90s, we had peer-to-peer networks, we have distributed computing. Because we have computers, we did not have enough bandwidth to do everything centralized, but with new connectivity, with mobile devices, we moved to another centralized way, another centralized architecture. Now, almost everything is centralized, is cloud-centric. Everything you see, everything you download, everything you upload, all your physical assets are connected to the cloud. But the question is it the best architecture for the IoT? The answer is no. We can do better. We can distribute the responsibility and keep the cloud doing great, analyzing data, allowing the connection of billion of devices and so on. But there are some cases where having everything in the cloud is not the best option. And IoT is one of these. Some IoT applications can take real benefit from this architectural shift. Just two real examples. I think that maybe some of you may have smart home assistants in their apartment, and they are mainly addicted to the cloud. They rely on the cloud to understand. They rely on the cloud to communicate. But if the cloud doesn't work, like yesterday, Google has some issue related to their main services, but sometimes it happens to AWS, to Amazon. So the idea is that I have an Alexa device close to me, but Alexa, to understand what I am saying, needs the cloud to understand. And if it understands, it needs the cloud to talk with my smart lighting system, because the connection among these devices that are both in my room right now are based on the cloud. So I speak to Alexa, Alexa talks to Amazon Cloud, that talks to Philips Cloud, that talks to my bridge in my room, and then finally, after these three steps, I can turn on the lights. But if the connection is not available, or if the remote service is not available, it doesn't work. Okay, you can say it is just a problem of turning on the light. Okay, but we had some other issues. For example, in 2016, Google has some issues related to their data centers, and in particular to the servers associated to the Nest thermostat, smart thermostat devices. The point is that Nest is a great device, really smart, but it has only one problem. It relies entirely on the internet connectivity. So if you doesn't have internet connectivity, or if the remote Nest application it doesn't work, simply the user can't interact and change the temperature in their room. I mean, you can touch the device, you can turn it on, you can change the device, the temperature, but it needs an acknowledgement from the server. If it doesn't receive an acknowledgement, it doesn't change the temperature. And it was a big news some years ago. So the point is, we have some core application, we have some core assets that needs to work in any case, also if we doesn't have internet connectivity, or we doesn't have, or if the remote services are not working. For these reasons,
Marco,
yes?
the same happened yesterday with the Google crash. Yeah.
Absolutely, it's an updated news. Yeah. So if you have a service that relies on the Google service to turn on the lights or everything else on data center, Google Cloud data centers, simply doesn't work for 30 minutes, 1 hour. If it is YouTube, maybe it's a problem, but if it is an industrial asset or equipment, maybe it's a bigger problem. During the last, I can say 5-6 years, the idea is to move the responsibility step by step, adding more layers to the architecture. So we move from a cloud-centric view to a fog layer and the edge layer. Sometimes you can see an overlapping between fog computing and edge computing. The general idea is to bring computation, so processing, networking, and by networking I mean intelligent networking. We can do 10 lectures about intelligent networking, is a really interesting and complex word, and storage. Okay, so the idea is that the possibility to allow a local interaction without the need of internet connectivity. And it is important to underline that Internet of Things, it doesn't mean that you have to be connected to the cloud. The terms internet in IoT means that you need to talk the IoT protocol, sorry, the internet protocols. Okay, so an IoT application can be fully local, but it is still IoT because if it supports internet protocols. Then if you have application that run in the cloud, it's perfect. But sometimes it is really important to have real-time capabilities, low latency, and you cannot rely on cloud connectivity and cloud services. So we need to create intelligent and distributed architecture. The main point is, if I have this kind of distributed architecture, I can do essentially aim to reach 4 points that I believe are really interesting, and I took them from the Edge Computing Reference Architecture from the Edge Consortium. The idea is that if I can work in this distributed environment, I can enable things to things interaction, so devices that can automatically talk to other devices thanks to standards, thanks to the use of common data format, and so on. Then we can have the interaction among things and local services. For example, a smart home can locally talk to its devices. I can locally have a local interaction between human and things in a local environment. I'm here, my smart devices are in the same apartment, so I can talk locally with them with Bluetooth, Wi-Fi, it doesn't matter, but it can be local. And of course, the cloud is amazing, it works great, it can scale, it can analyze a massive amount of data. So all these features are in the cloud, can stay in the cloud. So for example, I can train models in the cloud and then bring back them to the edge to be executed and to take decisions. In this picture, how digital twin can have a significant role. The problem here is that currently digital twin are mainly in the cloud, bringing with them the same issue that we have seen with cloud-centric approaches. And the main reason is that digital twin are currently associated to the vendors, so their aim is to bring the customer to their platforms. The idea is that if you keep the digital twin only in the cloud, you need to customize your application on the edge to interact with the cloud. So you have to change the devices to connect to create a twin, or you have to change some gateway in the middle of the communication to interact with the cloud digital twin. You bring a direct load on the physical device, because there isn't an intermediate layer between the physical and the cloud. You add complexity, and then you bring a strong bound with cloud platform. So if, for example, I have a device, a physical device, and I decide to connect to the digital twin of Amazon, I have to change the firmware of the device. But if tomorrow I decide to support, for example, also Google Cloud digital twin, I have to change again my device. So it doesn't scale. So the idea is that now we have also, sorry, this slide is related to the cloud point of view. But what happens on the edge? On the edge right now, without digital twins, we have a direct communication between people, services, application with the object. So I can directly talk to a physical asset in a smart home, in a smart building, everywhere. What are the problems related to this direct interaction? The problem is that objects are heterogeneous. So we have to handle this complexity where in the application or on the physical object. So we can decide, okay, we need only standard objects, so we have to replace them. We need to have only MQTT devices, or we have to create some intermediate level that is capable of handling this heterogeneity. So essentially, the risk is to bring complexity to the physical device or to the application. The other problem is that if we have a direct communication among application and devices, we have security issues, and we may have a direct load on the physical device. If it is a small device, how it can handle a huge amount of requests? And for huge, I can say 10 requests per second, 2 requests per second, if the object is constrained, if it has limited resources. So the idea is to use the digital twin in the cloud, but also bring the digital twin on the edge. And it is not a substitution of the cloud digital twin. It is a different replica. So we know from the theory that we can have multiple replication of digital twin. We can have multiple reflection. So we can say there is a physical asset, but we can have multiple twins. One of them will be in the cloud, on the edge, and the other one in the cloud. So bringing this intermediate level, we can decouple the responsibility. We can it will be a responsibility of the digital twin to handle the heterogeneity of the physical device, of its physical counterpart, and expose to the external world only standard protocols and standard data format. So if I decide to use only MQTT with, I don't know, a specific data format, this task is associated to the twins, not to the physical device. In this way, application can talk standard protocols, standard data format. And we have another advantages of we do not affect the core layer. So there is a protection of the core asset, and we can control the access, we can have security, and so on. So we can decouple this responsibility by adding edge digital twin. But as I said, on the other end, the cloud digital twin are great. We can have inventory. We can bring different digital twin at the same time. We can scale. We can allow remote access. And the idea is that the responsibility to connect from the edge to the cloud is not of the physical device. But since now we have a digital twin on the edge, this digital twin can connect to the cloud, to its own cloud, or to multiple clouds. So we can have standards. We can have a uniformity, we can have efficiency and real time, and we can have also interoperability with the cloud. And as you can see here, we essentially combined the two pillars of the IoT. We combined digital twin for cyber physical and intelligent interaction together with an architectural pillar that is the edge computing. Okay. the point is that all these aspects needs to create better application. It is almost impossible to think about a large artificial intelligence application in the IoT without having standard interoperability, data formats. It is really, really complex. But if we bring this architectural intelligence, it will be easier to design new smart IoT application. Just a few slides to underline how this revolution is happening right now. I mean, the 5G network, the next generation of cellular connectivity, it is not cool and interesting for the bandwidth. I mean, okay, we will have gigabits per second per device. Okay, we will have low latency. They are great. But since we will have 4K and 8K cameras on our smartphone, sooner or later we will use all this bandwidth, as it happens for 4G. The great revolution of 5G is the architectural revolution. 5G networks will be designed. They are not yet designed like that, but the standards support this kind of innovation, is designed based on edge computing. And in particular, we talk about 5G and MEC infrastructure, that means multi-access edge computing. The idea is that for some specific application, we will need super low latency. We can talk about tactile internet. So latency in terms of milliseconds, under 10 milliseconds. You think a robot for industry, or real-time streaming from an ambulance, or a real-time decision system for a vehicle. It is not possible to take this decision in the cloud. The step, the routes for the packets is too long. So we, thanks to 5G, we will move from a cloud-centric cellular infrastructure to a edge-oriented, where some specific services, some specific application, for example, digital twins, can be moved to the edge in order to support proximity, to support real time, to support ultra low latency, to support location awareness, because I am close to the device, I know where I am, and I can adapt my services according to the location, and of course to the bandwidth that we know will be a characteristic of 5G. So the idea is that MEC infrastructure and 5G will be the enabler for the next generation of applications. But I would like to move forward talking about 5G and show you how providers, in that case Vodafone and AWS Amazon, are already understood how the market will move during the next year. For this reason, they are trying to experiment AWS capabilities, cloud capabilities like Lambda function, moving services on the edge, thanks to 5G. So the cloud providers are understanding how the architecture will change, and this is a massive news for the community, and how it will change the overall design of the next generation of architecture. Talking about 5G and MEC, a couple of weeks ago, with Stefano Mariani, a colleague from our group, we participated to the hackathon, the DroidCon Italy hackathon. DroidCon is the main European Android developer conference, and this year they made a partnership with Cisco and Intel and Etsy and some other companies to organize a 5G and MEC hackathon. Allowing the developer to work for 4 months at least on a MEC infrastructure. So we participated and we won this competition. It was really, really funny to have the possibility to touch the technology and to work on the field. And just a few words about what we have done. Because we combined some of the things that I have showed to you today. So digital twins and edge computing, and the context was a vehicular application. Essentially, we created a prototype of a vehicular application, a cognitive mobility application that, taking advantages of digital twins edge computing, so low latency, allows to collect, analyze, and send messages related to, for example, smart parking, connected vehicles, in order to try to optimize the mobility of a smart city. From a technological and architectural point of view, we used digital twins on the edge. So we executed our digital twin on the edge to to virtualize roadside unit. A roadside unit is everything that is on the side of the street, and essentially generate information related to traffic, and be a camera, a sensor, something related to access monitoring, and so on. So we created a digital twin, one for each roadside unit and one for each vehicle. All these digital twins are responsible to handle the communication with the physical counterpart, and then communicate to an intelligent traffic information system that works with the platform. We worked with the openness platform from Intel, from Edge MEC solutions. So we created microservices to communicate for the authentication, location API. So essentially we deployed our designed application on top of this MEC infrastructure. It was really, really interesting, a really interesting experience. Okay, last thing, I will have some slides, but I will go through it quickly, but I will give you the slides. So the idea of this last aspect of the presentation is the interoperability. Interoperability in IoT is how we can handle the heterogeneity, how we can allow different services to interact automatically and seamlessly, without configuration, without human intervention. This is the real IoT. If I turn on a device in a smart building, for example, I add a new light or a new air conditioning system, I don't want to manually configure everything. I would like to have interoperability among services. And now interoperability in the IoT is really, really far. I switch directly to this slide. This is a slide that a picture that I took from Mozilla Foundation, the Mozilla that is behind, for example, Firefox. And what they have seen, and what the last year, there is a movement start talking about Web of Things. The idea is that at the moment, as I said before, almost everything in the IoT is vertical, is closed, is proprietary, is a vertical technological stack that starts from the point to keep the control of the application. And if I would like to talk to some other application, I need to add some connectors, I need to pay something. So the idea is to overcome this limitation. And for this reason, we can talk about Web of Things. I really like this sentence, because I totally agree with this sentence. At the moment in the IoT, we are really, really close to what we had before the World Wide Web. Okay, before the web, everything on the internet needs some custom connection to communicate. So there were proprietary interface, proprietary data format, and there wasn't a unified application layer for sharing information. And everything changed thanks to the web. So thanks to HTTP, to HTML, and so on. The ability to create a service and allow a seamless interoperability. At the moment, as I shown you before, to interact with the Philips lights, you need the Philips application. To interact with Amazon, you need the Amazon application, and so on. So if we can compare it with the web, it is something like, okay, to open the website of the CNN, you need only the CNN application. To open Facebook, you can open it only with Facebook application. It's not like that. You can use Chrome, you can use Safari, you can use Opera, you can use whatever you want. Why? Because we have standards that allows the interoperability. This is the missing point in the IoT at the moment, and I would like to give you this point. So the idea of Web of Things is to overcome this limitation and avoid and define some specification that can allow to create something on top of this fragmentation to allow the interoperability. This is what is doing, what W3C is doing, the consortium of web technology. They have created a working group called WOT, Web of Things. And the mission of the Web of Things working group is to fight against the fragmentation of IoT, defining some building blocks. They are not defining implementation. They are defining some specification that, if implemented across multiple platforms, allows the interaction. It is like the web. If you support HTTP, you can create a server, you can create a client, so you can be interoperable. This is the same idea for the Web of Things. I will go really quick on these slides. The idea of Web of Things is to define, essentially, to clarify the terminology. So how we can call each component in some clear and common way, to define common patterns of interaction. So to identify the common interaction patterns in the IoT and to define them. The next one is they try to define an architecture. So the building blocks of this architecture, the last document is from the end of April. So it is really, really new. And they are working on that right now. The other point is to define a description of an object that can be then applied to multiple implementation. So a smart light is a smart light. If it talks MQTT, CoAP, HTTP, over any other protocol, it doesn't matter. It will have a descriptor and multiple connectors that essentially explain to the external application how they can interact with it. Okay, so this is the main concept. And of course, they will also provide information about security, use cases, and so on. Last technical slide. This is an example of a Web of Things description. As you can see here, you can imagine it as some descriptor on top of the physical implementation. You can write this descriptor, for example, for your custom object, or for a Philips light bulb, or for any other standard or not standard protocol. So the idea is to define the context, to identify the name of the device, the type, the security levels that we have, the properties. So for example, we have a property here that is called status, and it is of type string. And to access this status, I can do a GET request using HTTP, because in that case, this status is mapped on top of HTTP, but it can be CoAP or MQTT. It specifies the action that you can do on the device. In that case, it is a switch, so you have a toggle, you can turn it on and off, and it is always an HTTP request. And then you can receive the events. So you can subscribe to event notification to receive a synchronous event, or you can poll. You can go by polling the status to receive the data. The idea, the really strong idea, is to create something that is standard and support interoperability. And this is another open point that I believe it is really, really interesting. Okay, since I believe that these topics are really interesting for us, for me, of course, we are doing research on that topics. So if some of you is interested to keep in touch and work on that topic, for example, for your thesis, you can drop me an email or to Professor Zambonelli and let us know that you may be interested to work with us on these topics. Talking about software project, so some of you may be interested to work on software aspect and maybe contribute to some open source project. We released 2 open source libraries. The first one is called White Label Digital Twin. It is a Java framework to create, we can say, automatically create digital twins for IoT application. And the other one is OpenS4J. It is the library that we created for the hackathon in Turin, for the MEC hackathon. We released it as a public project, open source project. And the idea is to create application on top of the Intel openness framework. So this is another opportunity to work on this project in the IoT and digital twin ecosystem that I just presented to you. Okay, that's all. Thank you very much. And if you have any question, let me know.
Okay, many thanks, Marco. Are
You're
there
welcome.
questions? Okay, I see no questions.
Okay.
But it's okay, but very interesting. Thank you very much. And as you said, this is another topic for possible thesis or projects. So
Yeah.
in case, keep in touch. Okay, thanks again, Marco.
Thank you very much.
And now we take a 10 minutes break, and we will resume at. There's one question. There are some questions. Another thanking you for.
Thank
Okay.
you to you.
Okay, so I'll see you back at 10 minutes, 15:30.
Bye bye. Thank you very much.
Bye.
Bye.